In this video, I want to discuss the concept of a half-life for a radioactive isotope. You see the definition there. It's basically dealing with a certain amount of time that it takes for, again, half of the sample to change. And when that radioactive sample changes, it could either be a new isotope or an element. Something else to note, that new isotope or element may or may not be radioactive. It just depends on the particular radioactive isotope you begin with. Down here, some of the half-lives are very long, up to the age of this planet for uranium-238, or very short half-lives, like you typically find for a radioactive isotope that's used in a medical setting. That makes sense. You don't want to ingest something that's going to be radioactive for years, let alone hundreds or thousands of years. You do not need to memorize these numbers. What I want you to understand is the basic concepts of the half-life and then how to handle some of the calculations. So in the graph here, we see one specific example, iodine-131. It's a common radioactive isotope. It has a half-life of 8 days. And sometimes that's written T1/2 8 days. From this chart, how do I know it's 8 days? Well, look where I start. Okay, I'm starting with 20 milligrams of the radioactive isotope. How long does it take for it to drop down to 1/2 of its original radioactivity, or the mass there? It takes 8 days. And you can see this, as you repeat every 8-day interval, then it drops down 1/2 of the remaining amount that you have. And that's why it does this like exponential decay. And this tail here will travel out, for a very long distance. Now, in terms of a calculation, let's just look at one of these. Let's look at B. And honestly, it doesn't really matter what particular isotope you're dealing with. I like the identity of it's cesium-137, that's fine. But really, the main thing that you want to know about is something about the mass and then something about time here. Notice in the problem up here, it actually tells you the half-life of this particular isotope. And for this class, one thing you're going to see is that going from the half-life to the amount of time that's talked about in the problem, it'll be some multiple. So basically what that means is that you're considering like masses at half-life intervals. And honestly, that makes the calculation much simpler. There's always a few ways to approach this. If you don't mind, let me just do this in kind of the simplest manner possible, just so you get a feel for kind of the logic that you apply really to any of the half-life calculations you'll see in this class, right? Again, after one half-life, how much of that 16 milligram sample is going to be remaining? You just divide it in half, 8 milligrams. Another half-life. Basically, going from 16 to 8, you divide by 2. So the mass or the amount, we're just dividing by 2. And you can do this, to any length of time that you want. Now, the reason why I stopped here is because that's going to give me my answer. Remember, I said that the amount of time that's going to be used in these problems is going to be some multiple of the half-life. Well, how much time does it take for this first half-life to occur? That's 30 years. How much time does it take for this half-life to occur? 30 years. Again, I'm just thinking about this in the simplest way possible. Every 30-year interval, you cut it in half. Notice now, 30 plus 30, 60, 90. Now we have a total, say total time, now is equal to that 90 years, which is what the problem is asking about. So after a 90-year interval, you're going to be left with 2 grams of the sample. You can pretty much use this kind of logic on all the problems dealing with half-life that you're going to come across. One other thing to watch out for are the units that are possible. Milligrams, very common. Okay, so units of mass, very common. Grams, milligrams, micrograms. You can also see units of activity. And for us, those units are Curie and a becquerel. All right, some metric prefix of it, like in that last problem we did, previous video, millicurie, microcurie, etc. And then the other type of unit that you might see is actually percent. And what you see here is, well, let me just sort of map it on top of this guy here. Like, I don't know what the activity is for, a 16 milligram sample of this cesium. That information is not given, but I can always figure out percent, right? I'm starting with 100% of the sample. After one half-life, I go to 50%, 25%. This would be 12.5%. And so percent can also show up as a unit with these types of calculations. But again, you handle it just like mass, you handle it just like you would activity. Divide by 2, divide by 2, divide by 2, for however many half-lives you need to add up with the amount of time that is being referred to. Thanks.